Hello and welcome to 16th lecture of course on data-enabled tribological engineering from experiment to predictive models. Topic of this lecture is a tribocorrosion, slightly different than what we have been covering earlier. We know that corrosion is one of the important problem which needs consideration. But how the corrosion really plays a role with the tribology, that's of more interest to us. So in this lecture, we'll be discussing corrosion and how it affects the tribology and how it overall causes the more economic losses and how do we really take a measures to minimize this kind of a problem. That's a part of this lecture. Let me start with common knowledge which we have, because corrosion has been in our life from class 8th onward, maybe say almost we have studied for 10 12 years, and when we read a newspaper also we read about the corrosion one way or another way. So what is a common knowledge to us? Let me maybe summarize in one or two slides. We say we know the chemical reaction between materials and its surrounding that will cause a corrosion. That means material chemical reactivity will play a role. If it is a potential is a lesser and negative side, it will be much more reactive. If it is a noble side, it will be lesser. Another one is environment, whether it is in presence of carbon dioxide, chloride, sulfur oxide, nitrogen oxide, or some sort of acidic environment, it will really play slightly different role. And operating temperature, more and more temperature, corrosion will cause will be more and more on the hard side. Now, what is the problem with the corrosion? It causes a structural integrity problem and reduction in strength. So both are important from economic loss point of view. It loses some structural strength when you have a big building, and its integrity or maybe say structural strength comes down with the time. That's important to consider, and then we figure out when to really demolish that structure. One rough estimation is that it costs around 1.5 trillion INR per year. That's a huge cost. And why we are saying that this cost? Now there are a number of methods, a number of parameter. We say corrosion reduces the performance. That means if in suppose initially there is some performance, with the time performance will come down. Another one that it really increases the maintenance cost. And last one is the safety issues. If we don't consider corrosion problem appropriately, then there will be safety issues also. And we history is full of such examples. It's a Bhopal Kand, or maybe say some sort of aircraft crash, or maybe some ship crash. Some way you will find a number several examples in this case. So safety becomes a major issue, and that's why we say it is almost costing 1.5 trillion INR per year. Now we also have learned something in our let me say from common knowledge. There are some metal called a noble metal, like a gold is a noble metal, platinum is a noble metal. They are non-reactive and they don't get oxidized even we are keeping it in the nature. So that's why because we know the novelty of these materials, often electrical contacts are coated with the gold. Gold plating is done to stop the oxidation of the surfaces, to reduce the possible damage to the surface. We don't use a sodium because we know the sodium has a lot of reactivity, and then we don't use in the common materials unless it is a compound with other. So that's why we know that NaCl is a salt, it's a compound. So the sodium doesn't remain in open form. Another one, often people feel that non-polymer, or means a polymer, particularly non-metals or ceramic or cement, they don't get oxidized or they don't get a corroded. No, it is not. They get also corroded, like in a polymers or ceramic, they swell, they soften, and they dissolve also when exposed to the acid and radiation, and they get damaged with the time. Another we have learned from our previous experiences that there are some material known as a passive material. What are the passive material? Passive material will have some sort of a resistance to the corrosion. So it's not that they are really resistant. They make a coating. Maybe say they get corroded, and then they make a thin layer on the surface which prevent further corrosion. So this is what we call sometimes is a sacrificial layer. This has been written here, the sacrificial layer. And then this sacrificial layer can be oxide, can be hydroxide, it can be some sort of salt. But good thing is that this sacrificial layer is a thin, adherent, insoluble and capable of quick self renewal. If the layer is getting dismounted or removed or scratched, then there is a possibility the layer again get reformed or maybe say renewed immediately, or self healing capabilities is there. If this kind of materials are there, then it will be very useful, and then we should use this kind of materials. However, it is also known that not necessary whatever the oxide formation occurs or whatever the corrosion product occurs, they are protective in the nature. We take example of rust is a corrosion byproduct. Of course, it is a mostly iron and steel or particularly ferrous materials, and then it's made of the hydrated iron oxide, which will be showing in the next slide or next to next slide. But rust does not create passive protection layer. That's what has been shown here. It does not create a passive protective film unless we use alkaline material in the environment. We use some sort of pH value more than 7. If pH level is lesser than 7, then rust is will continue, maybe the lesser rate, but it will continue, it will not stop. So these are the already known knowledge to us. And again, if you go through the history, we find that environment which contains water, air, fire and earth, everything is in corrosive nature. That's why we many times we say ancient Greeks believed that metals and alloys were deteriorated or damaged by the fundamental elements of water, earth, air and fire. And there are a number of examples. We already have seen the boiler tubes, they get corroded. You have seen patina, natural patina which forms on the bronze structures. We have seen also that if anything which goes in the foundation, because of the moisture, they also get corroded. And then even heat exchangers, so we have found that particularly if there is insulation below the thermal insulation, the water gets increased and get and oxidized, or maybe say form some layer of corrosive layer on the surface. So there are very numerous example of corrosion, and it is costing a lot to the nation. And then only thing is that how the tribology with the corrosion is playing more important role, or maybe say we need to minimize that role or minimize that synergy between tribology and corrosion. And one more thing in these days which is coming is industrial emissions, vehicle exhaust, and then other pollutants which are really corrosive in the nature. We know that sulfur dioxide and the chloride, or maybe say chlorides only, or nitrogen oxides, they are corrosive and then deteriorate the metal surfaces. And exhaust which is coming from vehicle, they contain a number of gases which corrode the environment. So basically even they corrode the buildings also. The huge buildings, they get corroded with the time. If they don't do a regular maintenance, then whole structure may get damaged or maybe demolished also, if we are not taking care properly. So this is the, we have enormous examples. Now we also learn from a literature that there is a something like a list, what we call electrochemical potential list, which is used for the quantitative analysis. It says that like gold has the highest chemical potential, positive, while in this direction is what we treat as a cathode, and this right direction we treat as an anode. We say that if the zinc is getting corroded, you replace zinc with iron, or replace with a tin, or replace with a lead, because the corrosion rate will come down. So this is what we have already learned. And then there is a report, economic impact report, which says that the corrosion in India costs around 1.67 lakh crore per year, which is much more than the budget of our education. Indian education budget was something like 1.13 lakh crore in 2023, while the corrosion cost to the product was almost 1.67 lakh crore, which is a more. And these are available in literature, and I just picked up to emphasize that these are very important aspects. And now coming to the tribology, say whatever the tribocoin pegs, if they are subjected to humid environment, we need to watch corrosion. Even sometime this corrosive element get mixed with the lubricant also, and lubricant is they're taking those pollutant or contaminant to the tribose surfaces. So we need to keep checking those things, and sometimes lubricant becomes more acidic in nature. pH level is lesser than 5. We need to really see what is wrong and how do we change. Lubricant moisture level increases, then again we need to change those things. And then if we find some material, particularly as I mentioned that we were using zinc and it's getting corroded fast, can we change to the iron, can we change to tin, can we change to lead, can we change to the copper? That way, so increase in this side method, we move from top, bottom to top to reduce the corrosion rate. Of course we need to know how this overall system works, and that's why this lecture has been framed or formulated, that we understand first what is the corrosion, how do we really remove those. So this is very important. Now this slide says that the cost of the corrosion is roughly 5.95% economic of GDP. Of course, 2.3% is a direct, which we really learn, and 3.65% is indirect in this case. And this is detailed. It has been detailed in 2009, one of the paper. And we say tribocorrosion is basically simultaneous occurrence of corrosion and wear. Corrosion is causing wear, and wear is causing corrosion, and this is a simultaneous, maybe they are working in a manner or synergy that will cause overall much bigger impact, much more losses. Now the whatever happened because of wear and corrosion, they are irreversible, so we can only reduce, we cannot really make things again. So that's when we need to really minimize this. So that's why I say, how do we reduce the synergy of this? Now of course the knowledge also says that if I use this synergy in manufacturing, I can develop a good manufacturing processes, then it is advantageous. So understanding science is important. What we are realizing is a harmful, it may be useful for the where the material removal is really required, like in manufacturing. So in those situations this combination or synergy will be very useful, but otherwise in tribology it is very harmful. So to understanding the science is important, and that will be very useful from manufacturing point of view, and useful also to minimize this economic losses. Now here we are trying to connect wear with the corrosion. We know that there are several types of the wear, but two dominant wear mechanism which really create a problem for corrosion is abrasion and erosion. We already know the abrasion is a two body abrasion or three body abrasion, and we have studied in earlier lecture. Erosion can be cavitation erosion, can be like a rainwater droplet coming and it is eroding surface, or sand particle and having some velocity is attacking the surface, so solid particle erosion. Basically they try to scratch the surface, they remove the material from a surface. Now corrosion, what the corrosion does, corrosion really converts a ductile material to the brittle material and create a little more porosity, and in that situation wear is much easier, or removal of the material from a surface is much easier. And if we don't have a tribology or wear phenomena, then it will be much comfortable situation, like everywhere when the corrosion gets finally to the passivation stage. You can see with the time, initially the amount of the corrosion happening is reaching to the stationary condition, it is not continuously changing. But when wear is happening or wear is occurring there, then this passive corrosion becomes a active corrosion. Reason being, whatever the protective layer is formed because of the corrosion is getting removed because of the wear. Again, the virgin material comes on the surface or is getting exposed to the environment. Another layer will form, again the wear will remove. So formation and removal becomes a continuous process, or they are having a synergy. Corrosion makes a layer which already is corroding the surface, removing the material from a surface, and this wear is removing that. So that continuous process happens, and that's why we say amount of the corrosion because of the tribology is continuously increasing. It's not getting satisfied or saturated at any level. For that purpose, we really need to do some good solution. We need to implement good solution to come up with that level. Now, another point, major point I am showing here, this is a big end connecting rod bearing. Big end connecting rod bearing, and this is a surface of the roller bearing. Now, in the situation both, we say that there will be, because of the corrosion, there will be loss of the operating clearance. Sometimes clearance increases, sometimes clearance decreases also. So whatever we are designing, whatever we have designed, it is not going to be the same. If clearance increases, again problem. Clearance decreases, that also is a problem. So this is a very important, that whatever we have designed, that is going to change, and that's creating more problem. And we know very well that corrosion again doesn't happen in even manner. It is a remaining uneven manner. You can see here big and connecting rod bearing. You can see the contact and the patches of the corrosion. They are not uniform. They are not same as the whole circumference. They are there, but again they are going to be creating more like a misalignment, some disturbance, some surface roughness. We already know that if there is a surface roughness feature comes, tribology is going to get punished, or maybe say the bearing surfaces are going to get punished because of the surface roughness. Any misalignment which will create more problem, load carrying capacity will come down, friction will increase, wear rate will increase. So this corrosion brings more and more non-uniformity on the surfaces, causing a more and more problem, increases the surface roughness also. Now here in this patch, you can see here the stationary roller element bearing and patch are the formed. After that, naturally the vibration level will increase. With the increase in a vibration level, naturally impact will increase and the bearing life will come down in this manner. So that's why what we are saying, that corrosion creates a more problem in tribology in this case. Of course, by chaining the clearance, and whatever was even the ductile material earlier becomes a brittle and gets ruptured or fractured at much faster pace. Another one point comes, a corrosion rate increase with operating temperature. Now here, if the bearing clearance becomes uneven and it is not the designed one, the bearing temperature will increase, and that because of corrosion has caused a increase in a temperature. Now with the increase in a temperature, that will again increase the corrosion rate, so it becomes a catastrophic. And then the corrosion is increasing, the changing the bearing clearance, bearing change in the bearing clearance, increasing the temperature, increase in the temperature causing the corrosion, further corrosion causing the bearing clearance. So quite possible and certain failure may occur also in this situation. So we need to see how to really accommodate this kind of corrosion and reduce operating temperature. Now I picked up a few things from literature to just to demonstrate. You can see here in one case, nickel chromium was used, and with increase in temperature from 30 degree to 60 degree, corrosion rate has increased significantly. Of course, the corrosion rate has been given as a GMD, that's a gram per meter square per day, which is increasing. Now if nickel chromium is changed to the copper, you can see that it's stationary, or maybe that is not changing that significantly, almost insignificantly. So this is important when we do a testing of materials and then tribo testing of material in the presence of corrosion, that will help us to mention very clearly that the material which we have selected or tribo surface we have selected is working properly or not. One more thing comes, corrosion rate. When we see a normal way, sometimes people say that increase in the corrosion rate happens, but the saturation level comes, and after then again the corrosion rate comes down. This is not a cumulative corrosion, it is a corrosion rate. Now here the corrosion rate is coming down, and what are the reason they have given? They say corrosion product and the film formation occurs and it reaches to one stable condition. Now once it is a stable condition and the virgin surface is not getting exposed, then in the situation the rate will come down with the temperature. But in presence of the tribology, in presence of the wear rate, in presence of the abrasion, in presence of the erosion, whatever the stable film thickness which has been made will get ruptured, will be removed. So instead of going down this side, it will can again increase in this manner. So this is with a tribology. Say without wear, and this will be with a wear. So that's why there is a synergy between tribology and wear, also between corrosion and wear, and that is very important to understand. However, before exploring all those, we need to understand what are the dominant cause of the corrosion, dominant types of the corrosion, so that we can think which corrosion type is much more significant, and we need to act on those corrosion. The three main type of the corrosion are chemically induced corrosion types have been given here is aqueous corrosion, high temperature corrosion, and biochemical or biological corrosion. So we are not going to discuss about the biological corrosion or biochemical corrosion. We'll be discussing only on aqueous corrosion and high temperature corrosion. Aqueous corrosion because in most of the it is a humid environment and there will be moisture, and if we are using the metal, chances of the metal getting rusted is there. Even in case of the ceramics or cements, they also change the structure and microstructure, and then they go much faster deterioration compared to the in absence of the moisture. Another one is a high temperature. In the case of the high temperature, oxidation also happens fast, sulfatization also happens faster, and chlorization also happens faster. So these are the important aspects to understand. In case of the environment, of the corrosion environment and temperature, corrosion rate will increase significantly. Now if we try to see in a slightly different manner, we say we can divide from tribology point of view in five category. One we call a uniform corrosion. Of course, as such there is nothing called a uniform corrosion. It is basically aqueous corrosion which is common. One is a galvanic corrosion. Pitting and crevice corrosion is also important, and last one is a stress and the corrosion cracking. So these are the five type of corrosions, and as I mentioned that mostly we will be what we get in environment is something like aqueous corrosion, which also people say rust. So rusting is very common because we are using mostly the metals. Even in polymer on cement or ceramics case also the aqueous corrosion is common. And coming to the pitting and crevice corrosion, we say it is a localized corrosion and the impacts are significant. Reason being that pit formation or crevice formation happens whenever there is a slight change in a manufacturing, a slight defect in manufacturing, and even that small defect causes a major issue. Even you cannot detect easily. That's why we require a sophisticated methods to detect the crevice corrosion or pitting corrosion. Last one, as I see the stress corrosion cracking, many times we say the most of the failure happens because of that. Corrosion is already there. It will change the ductile material to the brittle material, and under the brittle material when subject to tensile stress will cause the failures. So most of the time the failure happens because of the SCC or say stress corrosion cracking. So this is very important. Now let me take one example of the rust. What we are using the word aqueous corrosion. Leakage first is the iron getting oxidized and making ferrous oxide. Till this there is no issue because this ferrous oxide is kind of protective layer. Now here the polar material comes, water comes, and it becomes an electrolyte, and when the electrolyte it makes a cell, and that's why we say hydrated ferrous oxide becomes a rust, and this is a form of the rust research. Now here the number of cracks are developed, number of pores are developed on the surface, and again the water gets ingress, again makes another layer, another layer, another layer. So that is more problematic. Making iron oxide is no issue, But in presence of the moisture, in presence of the acid, in presence of the chloride, then there is a problem, because electrolytes are provided to the cell, and then the rapid corrosion starts. So that's why we say in acid case, the lower pH level, or in the case of the salts, they become a very corrosive. Reason being that more very high concentration of hydrogen ions are there, and then it will speed up the corrosion of the metal. Now, because the chemical processes between metal and electrolyte happen more quickly, particularly temperature, the temperature increases, then if you want to really do the check, you can find out the accelerated test, or maybe you can find out the accelerated rate of the corrosion. So sometimes people want to do accelerated test, they use temperature as one of the criteria. 30 degree, what is the corrosion rate? Now if it would have been 50 degree, what is equivalent to the how the much increase in the corrosion happens? So that can be done. However, at the temperature, with increase in the temperature, there will be acceleration in this case. To understand this phenomena, we can take example of electrochemistry, where we know we have already studied something like anode and cathode. We know that anode is generally loses a material and make a metal ion, which may get dissolved into the electrolyte, or make a bond with OH, the ion which are present there, and cathode is basically receiving of the electron. But this will process a kind of electric current. It can be DC, it can be AC, and that may be deteriorating, or that causes the problem. Now if we want to really break that, you either change a node, or you change a cathode, or you change a electrolyte. That's what we, from tribology point of view, we say that how do we really avoid and how do we make a system in a proper way, so that this process can be minimized to the almost negligible level. So that's why we say position of the metal in electrochemical series indicate that if I replace zinc with a copper, I may get a better performance. That means, and then the zinc can be replaced with a cathode, with copper, and then overall rate of the corrosion can come down significantly. However, we can try with zinc and copper, and that is what we call as galvanized corrosion, and maybe can be also tried with a faster deterioration of the zinc, and then copper remaining ineffective. That's what we can try when we go for the two metal corrosion. Is here in for aqueous corrosion, we are looking at the only one metal, so replacing zinc with a copper will give better results. But in galvanized corrosion, then zinc also can be involved, copper also can be involved. We can see in presence of the zinc, copper doesn't get corroded, it is the zinc which will get corroded. Now just to elaborate little bit more, what I mentioned here, bulk iron and getting oxidized, there's no issue. But in presence of the environment, salt environment, contaminated environment, or maybe some sort of the crack, which is allowing the environment or the situation to form electrolytes, or in there's a cell or electrochemical cell, then there is a problem. Reason being that in the situation, iron will become anode. It will start losing the electron, and that is a very important. Loss of electron from iron will be problem. In the situation, what we can do, we go ahead with a smaller cathode dimension. If the cathode dimension are smaller, then there's no issue. But sometimes cathode dimension are much bigger than anode. In the situation, problem will be there. So this is where we need to play a role. Now here it has been shown here very clearly the how the cracks are getting generated, and then kind of iron oxide, and then the maybe water gets ingress in this kind of patches, and it gets it maybe say worn out very fast. Now if there is any cylinder which is getting into and out, naturally the wear rate will be very high, and then there will be the continuous exposure of the virgin surface getting oxidized and getting removed also. The clearance will be much larger. So this is what we need to avoid. And sometimes water gets ionized, and we say that will water when get ionized, it gives a hydrogen ion and gives a hydroxide ions. Metal surface is very keen to get a hydroxide ions like iron. it will immediately react with OH ions. It will also release positive ions, maybe say iron will release iron. So that creates a more chemical action. Now we want to reduce it, then naturally electrolyte has to be changed or need to be removed, or the make in a manner that this action doesn't happen completely. So to avoid that, we can use some sort of corrosion resistant metals. We can apply a coating, or maybe the painting, or maybe the some sort of a plating to protect the metal surface. Or even we are thinking about a lubricant, in the case we can add a corrosion inhibitors to minimize the corrosion rate, or avoid the impact of the corrosive media on the metal surface. So this is an important thing from a tribology point of view. We need to think about corrosion resistant material, applying coating, as I say plating also is possible, and then we can add additives, something which we know as a corrosion inhibitors to electrolyte to prevent the aqueous corrosion. So this is an important aspect. Now coming to the galvanic corrosion, as I mentioned that if we know corrosion is increasing, we need to utilize the knowledge in appropriate manner. Now here the galvanic corrosion, we say it happens when two different metals or alloys having a two different electrochemical potential, they come into contact, and then electrolyte has to be present. If there is no liquid, there is no media, then process will not be there. Now, if we are using more active or more reactive metal, which is in a less noble, then it will get corroded. And I give an example of the zinc and copper. Naturally, zinc will get corroded, copper will not get corroded. Reason being that the zinc is less noble compared to the copper. Another point comes shape and the microstructure also play a very important role. When we are using the microstructure, even a surface roughness plays a very important role, because surface roughness has a peaks and valleys. If this corrosive media or water gets into the valleys and remain for some time, then it is going to give a electrolyte space and make a complete electrochemical cell, which is not correct. So what we say, the relative surface area of the two metal in contact or affect the rate of the galvanized corrosion, that has been demonstrated here. You can see there is a cathode and there is an anode. Cathode, which has a better electric potential, which is a more noble. So cathode is something which is more noble, and anode which is a less noble. Now if we make this kind of a structure, the anode is a bigger size and cathode is a smaller size. That's why we say large anode area, small cathode area, showing relatively insignificant attack, right? So the corrosion rate in this situation will be lesser. Now just reverse situation, if I use this as an anode material and this as a cathode material, then what will happen, the cathode area is much bigger. Large cathode area, smaller anode area, showing relatively pronounced attack of the fastener head. That means here the fastener head will be getting much faster corroded compared to the cathode area. So we need to really utilize our science in a proper manner to get a better results. Like in this case particularly, if I use brass material, which is more noble compared to the mild steel, in the situation that this screw will not get corroded, only nut will get corroded. Now other side, if I change this as a brass nut, and the bolt will be of the mild steel, then whole bolt will get corroded. That's an important aspect to consider. Even if I use a washer, something which is a more cathodic film, then it will get much faster wear out. However, if we remove a complete electrolyte, then there is no issue. But situations are unforeseen, and we need to really think which material should be cathode material, which material should be anode material, and then take a right decision. As I am given an example that most of the electronic circuit, they do a gold plating, so that there remains in a cathode form, doesn't form this corrosive product on surface. So that's very important, and then we need to really keep this in a mind that whenever we are designing from topology point of view, we need to keep cathode material which really has a more significance compared to anode material. And another possibility, the surface imperfections like scratches or cracks or roughness should not be there. However, it is going to create a localized corrosion. Localized corrosion can be pitting corrosion, can be then the crevice corrosion, and then in both the cases both are very harmful, what we call a silent killer. We will not know the metal is going to get completely disintegrated in a number of parts. So that's very important to consider. Now localized first corrosion is a pitting corrosion. What we are saying, the small flaws on the metal surface such as the scratches might serve as a site of corrosion, and in this picture it has been shown there is a metal surface, there is a coating, and there is a some sort of disruption in the coating, maybe some sort of micro crack or some in the portion where the electrolyte can get ingressed. If the electrolyte can ingress through this, it will form a kind of electrochemical cell over here, and slowly the pit will formation will increase. So this is the important aspect. And then finally initially this small crack we will not be knowing, we will not be able to detect, but subsurface level the the damage is happening, and when damage is significant, and finally we may get a surface something like that is getting completely corroded at our area, which is we cannot replace, maybe we need to change complete part, we cannot repair easily. So this is where we need to see, as I mentioned, it is a silent killer. It damages a material silently, will not be knowing, and suddenly material fails completely. So what we are saying, the pitting happens when a passivinating, maybe say a passive layer which gets formed on a surface, or the coating which we are providing fills and expose small patches of metal surface to uncontrolled corrosion. Once the corrosion starts, after that it is not going to stop. Reason being, the smaller portion is which is getting in, that is getting a kind of anode, and when it gets anode here and whole surface is acting as a cathode, naturally the wear it will be much faster. And we say that cathode has to be much smaller, and as a previous example, we say that cathode has to be much smaller than anode. If we are able to keep that, then the surfaces will be in a good shape. Otherwise the wear rate or the corrosion rate will be much faster. We say unbroken passivating film. The first phase of if there's no pit as such, first phase will start with the pit creation as a kind of nucleus or small patches or maybe say scratches in this case. Once that is formed, after the pit growth happens, and then that cannot be controlled. And then initially, as I say, the metal surface will appear to be unharmed by immersion in a corrosive media for some time, and that can be known as a induction period. In that period nothing will be visible, and then the cracks will increase in a size, and once it is done, induction period is over, then we can find out there is a number of critical size, or maybe say crack have grown beyond critical size, and then there is a formation, the pit formation will start. So if you want to really minimize the pit formation, we need to see that whether remedial action can be done, or there is a sufficient time. If there is some sort of disruption on the coating or some sort of oxide, the damage occurs, then it should be repaired immediately. But we know in the tribology, particularly abrasion wear, erosion, this phenomena will be dominated. More and more rupture of the oxide layer will occur, and then we really need to think from a tribology point of view. The surface softness should be smaller. Particles which are coming and trying to erode the surface should be minimized. Velocity should be changed. Angle of attack should be changed. Those things are important when we consider these aspects. Now we see the on formation of pit on the surface. As I say, the pit, as I mentioned here, is a pit formation. It becomes a anodic, and on the whole surface this becomes a cathode. The whole surface becomes a cathode. Then the nearby metal surface serves as a cathode. As the anode area is much smaller than cathode area, So that's why we say rapid corrosion inside the pit can subsequently proceed to its depth. That means it goes deeper and deeper because there is a anode, there's a electrochemical action is continuous, and pits gets deeper and enlarged, which can result in a considerable subsurface corrosion even if pit surface aperture is relatively small. That means on the top we are not able to see much variation, maybe the crack size is smaller, but because electrochemical reaction is happening inside that surface, so that's why we are saying subsurface corrosion is going to be considerable, and then will is create a more problem. Or another one, once a pitting corrosion is start, formation of tiny bits or cavity on the metal surface start appearing, and that has been shown here that there are a number of pits on the surface. Maybe in and when the pit formation occurs, nothing was visible, and suddenly it has gone to the so many pits and is spread in a significant manner. And one second thing which I mentioned, the crevice corrosion. Uh, Crevice corrosion is basically kind of a very tiny voids, even much smaller than the pits form. Have observed particularly wherever there are welding, and particularly when there is no appropriate welding. When we have seen the number of bridges, when the two surfaces are they are trying to connect, they will so use some sort of spots, and then they we will find some cracks are there, or maybe some holes are there and through, and that can act as a kind of and the surfaces which can restore the water, or and the within the contaminants from environment, which can make a sulfuric acid, carbonyl acid, or something like that. Those things are possible. So that's why we're saying that crevices are tiny voids that form between interacting surfaces during joining. I have observed particularly in welding case, even the gasketing, when we do again, if the gasket is not properly aligned, there are some sort of pockets, then again problem will come. And similarly threading, or even the manufacturing surfaces, when we are going with bimetallic, trimetallic, and there are some sort of voids, that will create some sort of a crevice corrosion possibilities. So crevice corrosion occurs when a metal surface is exposed to corrosive environment. As I say, water is a corrosive environment, salts are corrosive environment, water with SO2, carbon dioxide, or environment, or HCl, or with the only chloride, they are corrosive environments. And then the concentration of corrosive environment substance will increase within the crevice, and that's where we say that because of differences in outside inside, this works as a electrolyte, and then major thing is that electrochemical action keeps on increasing, and that's what is called accelerated corrosion happens because of that, which is within a small tiny 1 micron and then the hole, and below that we may find that whole maybe 100 micron pit is getting formed. Quite possible it can start from a crevice corrosion, goes to the pitting corrosion also, there is a possibility. And as many times we have observed in the manufacturing time this happens. So whenever the skilled and unskilled thing comes, people who are skilled in welding, they will do good welding. Unskilled welders, they will leave some gap and will cause a failure. And mostly we've seen that big bridges and all, if the had been done or repair has been done by the some unskilled person, and this kind of problems will be there. So what we can see, the crevice corrosion is frequently difficult to detect, because naked eyes we will not be able to detect, or maybe you need to use some sort of non-destructive testing, and can proceed quickly because the corrosion product concentrate in a limited space, because whatever the ions are getting formed that remain that in space, and that's why we say concentration increases, it worsens the condition for the corrosion. This corrosion can eventually cause a metal penetration and perhaps a catastrophic failure. This is important. Something which was not visible from a top, and suddenly whole big pit comes out, or maybe the strength has come down significantly. So this is important to consider. Now we are saying accumulation of chlorides or other corrosive material, maybe as I said that there are number of gases, contamination in the environment, they can react with the water, and then they can make some sort of acid. They remain in this kind of crevice for some time. Naturally, they will increase the corrosion rate significantly. So what we say that to prevent the crevice corrosion, we really require a good design consideration. And then major thing is that we should not have a stagnant spots. How what are we why we are saying this? Reason being, the welding after done, if it has been we use a sealant, even the sealants are not going to what we say handle stress, but can prevent ingress of the this contaminated or pollutant water, or maybe say water ingress. That is going to help. Even many time people say sealant, so why we do use a sealant? To avoid ingress of the this kind of moisture or acidic, and which creates a problem. Or after doing all this manufacturing, we do a top some sort of protective coating that will also help us. As I say earlier, that in case of the oil or lubricant, we can use the corrosive inhibitors which can really reduce the chances of the corrosion. So protective coating is a one. Sealant, whatever we do, wherever we find there is a possibility of the gap, we seal that gap so that ingress of the water or corrosive media should not be there. Then it will remain safe. Of course, we keep checking using some sort of technique to measure that what is really happening. And last, which is much more difficult, is a stress corrosion cracking. We have seen a circumferential stresses, and then which becomes a tensile into nature. And if there are some sort of cracks, and electrochemical cell formation occurs there, and it is also subjected to stress, particularly tensile stress, then the form and this damage will be much more severe. So that's why we say stress corrosion cracking happens when a material can be anything. We here can be titanium alloy, which is very good as such, steel, stainless steel, they are subjected to both. That means there is a synergy. It is a one is that the tensile stress and corrosive. Now, tensile stress also occurs because of increase in the temperature, or some sort of the residual stresses, or maybe when there is a applied load is going suddenly, maybe getting misaligned that time also. And corrosion can be any kind of corrosion. Of course, so we also understand the alkaline media may not give it that kind of problem compared to the saline or acidic nature corrosive environment. And here the typical has been shown that the chain which was under tension breaks in between also, because of the corrosion, and the tensile stress is applied in both the places, or maybe it has been applied simultaneously. So if I try to summarize the tribo corrosion, what we say, the where is we need to keep into account the where is happening. Now how do we say there is a one surface here, other surface here, and corrosive media over here, and there is a some sort of a protective coating, or some sort of passivating layers over there, and it's getting ruptured too because of abrasion or because of erosion, right? But this will occur, and there's a possibility of the new oxide formation. Yes, no, we are not denying that the new the layer will not get formed, but whatever the time delay in a new formation and the rupture of the oxide film, if there is a delay, then there will be possibility of the ingress of the water or corrosive media into there, and making an electrolyte cell or electrochemical cell. So that's why we are saying here the wear assisted corrosion. There was a no because of the wear phenomena, the this oxide layer got removed from a protective layer got removed from a surface. Now because of that, what this corrosive media get ingressed into that, and that is creating more and more the corrosive product which are brittle in nature, and also can get removed easily. So now here the main difference comes. Quite possible corrosive media reduces the friction but increases the wear significantly. Earlier we were talking about friction and wear together. Here in this case, quite possible friction comes down, but wear rate will increase. So this is important. So that's why we need to measure always the friction and wear simultaneously. Anything which is increasing, we need to note, and then we need to take appropriate parameters or appropriate design features to nullify that effect. So we say wear assisted corrosion compared to passive or oxidized surface. New surfaces, which are maybe the virgin surfaces, they get exposed to the corrosive media, and that they are much more reactive and susceptible to corrosion. So here, because of the wear, surface gets exposed to the corrosive media. However, there was an oxide layer. Prevention was there. Corrosive media was not supposed to do anything in that. But because of the wear out, corrosive, it gets exposure to the corrosive media. Corrosive media forms a layer, changes the clearance, reduces the load carrying capacity. Again, the wear rate increases. So this is a word of synergy we are talking, and that is going to really help each other. So what we say in this is abrasive wear removes oxide layer through asperity or hard particle. That's asperity is a two body abrasion. There's a three body abrasion, and then make surfaces susceptible to corrosion attack. Another possibility is a mechanical erosion. Erosion can be cavitation erosion, fluid erosion, particle erosion, or solid particle erosion that will get impacted by the fluid flow or solid particle. Removes a protective layer, exposes a newly formed metal surface or virgin surface to corrosive media, so that a new layer gets formed on that. So this is, now if we try to show figurative manner, say here the corrosion unaffected by wear, when the surfaces were not wearing out and the only layer got getting deposited. But now because of the wear, what will happen with cut form, again it worn out completely, then cut form, another cut removed, another layer got formed, again it got removed, another layer got formed, and then removed. But if you look at the cumulative, this is a removal, this is a removal, this is a removal, the depth of wear is significant. So that's why the synergy is, when we use the word synergy between the wear and corrosion, then overall the depth of wear increases significantly. Now one interesting point comes here, that whether everything can work as a electrolyte media or not. What we have realized, that when we use a strong sulfuric acid, it doesn't get into the anionic form, and then reason, because of that, strong sulfuric acid or any strong acid will not harm that much compared to weak acid. So this is an interesting point. We say that when the weak sulfuric acid, it has a water content also, and that allows the much what is it, corrosive media becomes a much more corrosive media compared to the concentrated sulfuric acid, and or maybe say even any other acid, because we really required anions or maybe say iron and to really increase the wear rate or corrosion rate. If you are able to control those, if you are able to keep a hold on that, then overall corrosion can be reduced, wear can be reduced. So this is very important. Now when, as I say, that whatever action we do, it needs to be tested. So that's why we say corrosiveness of the material under control condition to determine the efficacy, what is the effectiveness of that whatever we are doing, and how it will be, the lifespan will increase or decrease. And when you are choosing a different material, we are choosing different lubricant, we are choosing different environment, what is going to happen? That's why the wear corrosion testing is required. And then even we are trying to go ahead with some sort of a coating, or we are choosing nano material, that needs to be tested, and we need to figure out whether these are effective or efficacy is good and lifespan is increasing significantly or decreasing significantly. That needs to be tested. Or even sometime we want to go for accelerated test, and we say wear test is one, but when I add a corrosion, it is going to increase significantly, so I can treat this as a accelerated test. So instead of running the setup for the 18 years, I can run for the 1 month. That's also possible. So understanding first, and then making good models and projecting in appropriate manner will help. So this is what we say when we can identify the potential failure modes, and then we can really develop some sort of mitigation strategies how to minimize the corrosion and wear together. Now, to mimic the corrosive, particularly marine environment, in our lab, what we do, we use some sort of a salt vapor or salt, and then in a closed chamber, so that can be mimicked. That means we understand what is really in marine environment, how much salt is really required, or is a salt vapor or salt water, that can be done. Now, if we want to do acidic test or corrosion the test, particularly for it has to be determined for how much time, is it for the 10 hours, 20 hours, 30 hours. So that can be done. Immerse a specimen in a acidic or corrosive solution for some time. It can be days, it can be hours, it can be months also, to determine its resistance. And then we can check weight or volume. I prefer volume compared to weight, but if it is a significant, then we can go ahead with the weight also. Or appearance, microstructure, or some sort of a structure change. One more thing is a mechanical property, how the mechanical properties are changing, because we mentioned about the tensile stress. If the tensile strength is coming down significantly in corrosive environment, that need to be notified. Another one, we say that accelerated corrosion testing subject material to condition, particularly when we don't want to do for the long term corrosion test, we can go ahead with accelerated test. As I say that we can increase the temperature, we can increase to some percentage of the acid, or reduce the pH level. But again, as I mentioned, that we really require electrolyte which really enhance the chemical action. It should not that we go for the higher concentration like a sulfuric acid or nitric acid, and then overall reaction comes down. That need to be also checked properly. Another one, we say electrochemical measurement needs to be done to really figure what is the corrosion rate, what is the corrosion potential, because we know something from a list what is a published, but whatever the material we are getting, we may not have a same value of electropotential. And then coming to the effectiveness of the corrosion production measures. So what we do, some sort of testing procedures are there. We say potentiodynamic scanning, electrochemical impedance, or polarization resistance instruments are there, which measures that what will be the these characteristics related to the corrosion, which will be useful. Now coming to the temperature, which is the high temperature environment, particularly in power plant, or as you say exhaust system, the temperature goes on higher side. That then in the situation, whatever the material which we are going to use, it should be tested. Now here the abrasion also will come, or erosion also will come. So we try to simulate the same situation. We do have a setups for the abrasion and erosion. Those can be tried, that together where there is a synergy, how fast wear will occur, how fast corrosion plus wear will occur, those need to be tested. So testing is very essential for this kind of now one is a radiography testing people do. I'm just going to describe in one or two slide on the particularly UT, that's ultrasonic testing. We use two sensors. So one sensor sends a signal, other sensors captures the signals. Now in ideal situation, perfect case, we know that what will be the microsecond, how fast we should get the response and what kind of response we should get, and we compare with the actual case. So we have already tested case, perfect case, and we compare with the other test. So here particularly now they are trying to figure out this steel bar which is used for the concrete purpose, then how fast it get deteriorates and whether there will be any crack formation or not. So that's why the UT has been done for that. I'm picking up this example from one of the publication, which was a 2014 publication. The title of the paper is Evaluation of Corrosion Induced Crack Rebar Corrosion by Ultrasonic Testing. And then they use a concrete prism, and the dimension has already been given over here. And then they use the 50% there's a concrete ratio that has been mentioned. Now what we are seeing, the corrosion of steel reinforced bars particularly shorten the useful life of concrete building. Now if there is a corrosion of the steel bar, because we use steel reinforcement bars to increase the strength, but this reinforced bar gets corroded, naturally the useful life of the concrete building will be reduced. And corrosion of the rebar and development of corrosion induced cracks. And then, naturally, even if you use a cement, there should be some crack to get ingress to the reach to the iron. Otherwise, it will not be. So, if we are able to find out those cracks, it is not only the rebar corrosion, even the how the passage happens, whether concrete is getting fractured or getting some sort of cracks, that also need to be detected. So that's why we say that induced cracks in normal and accelerated test, we can use accelerated test, and then we will try to figure out using the UT. When corrosion is present, we say the amplitude of recorded wave is reduced compared to when it is absent. Even the time is one, time will be lesser, and then here we are saying amplitude will be and then when there's no crack, the time should be much lesser when we are getting signal. Whether time is also increased and amplitude is decreased, both are indicator that there is something wrong, and then we do more and more testing and the calibration charts are there. If we compare, then we are able to compare these things. So we say ultrasonic wave attenuation but the reduction due to corrosion induced cracking can be detected by analyzing energy spectrum. This is another method to connect with energy spectrum. Now in this case, whatever has been done, as I say that water to cement ratio of concrete is a 50-50%. They tried for 28 days, because every concrete has some sort of curing time, and then they use a 28 time curing period, so that concrete samples gets formed, particularly in Portland cement. And then during maybe say once the curing time is over 28, they were subjected to the electrolytic corrosion test, by submerging in a water with a saline water, and that's why the 5% saline water was utilized for this purpose. That's why using the containing 5% and this NaCl water with electric density. Now here the current also was passed for the doing accelerated test to figure out what is really happening. As I mentioned earlier, the two sensors, they one sensor sends a signal, other sensors receives it, and that's why we say receiver predominantly detects the reflected waves from a specimen boundaries and rebar. So this is the test they do, and just showing the response. They are shown the crack formation in this acidic situation or accelerated test. They got around 1.4 mm width crack after 98 days, and this is done. Now here you are able to see that before electrolytic test, what response they were getting, the black color. After 24 days elapsed, there is a somewhat response change, slightly lesser. So you can see this is a peak, a black color peak, this is the orange color peak, and this is a green color peak. So as it was mentioned, the response comes down. As a response comes down, naturally something is wrong, and then if it is a calibrated, it can be simulated, then there are possibilities of the crack over here. So this has been done. So what we say that after 24 days of corrosion test, amplitude of waveform is a lower, that has been shown, that this is the black color, this is the orange color after 24 days, and this is after 90 days. This finding holds true from 24 days to 90 days, indicate that a reflection is scattering due to the corrosion induced cracking is occurring over the time. And then they use a P wave. So in UT we have a two waves, one is a P wave, another S wave. S is a basically shear wave, and P is basically normal waves, compressive waves. So they use that, and then wave velocity they decided something like 4 meter per second. And then arrival time, we say rebar arrival time projected was around 20 microsecond at this velocity, but reflection from a bottom a specimen is predicted to occur at roughly 75 micron per second, microseconds. So time has increased, and this has caused a problem. Now this is what we are mentioning here. P wave is a compressible compressional waves propagate through the liquid. And why we are using P wave? Because it can be used in all the media. If there is a gas or crack, even this media it can pass through that easily and gives a response. Why if we use only the shear wave, then it will only propagate through the solid. It will not come back easily. Maybe if there are cracks in the situation, the P waves will be better option and will give them better results. Now, when we go for the eddy current testing, what also mentioned very clearly that how do we test particularly the early stage of the corrosion. Here this is where we are talking about now in the new testing. Of course, the radiography is one of the test, but there is another test what we call a eddy current test. We say that whether increase in a thickness, what kind of response will be different, will be there. Now another point comes then if surfaces are the coated, particularly even in steel surfaces, in concrete or any other surface, what will be the happening. So basically both the surfaces corrosion has been tested with a sea related marine environment, and then shown here that some patch A and B, and this is the protective one, or that's a coated sample, and this is an uncoated sample. What is happening. So these people did some sort of a structural steel the material utilized S275, and then they test it for the months, like a 1 month, 3 months, 6 months, and 10 months for the both coated and uncoated. That's what has been given the time, and then they give a samples also 1, 2, 3, 4, 5. These are all uncoated, and then this is a kind of coated with a non-conductive paint that the conduction should not occur in the situation whether they can provide some sort of safe thing or not. And the last one is a coated. Now here you can see when they are using eddy current, they are not finding significant variation. Now here you can see uncoated the circles are there, and there is a big difference in the values also. Of course they measure around 16 values per measurement 16 times, and then they are quoting average value, and we find particularly in here you can see there is a overlap. So that is not really giving a good difference, and that's why we really, when we go for the instrumentation, we really require a signal conditioning, we really require a good methods to minimize the noise, and that will be done in the future lectures. Now what they have measured here, the B norm which has been plotted. How do we go ahead with the B norm? It is basically they initially capture the reference signal when the material is not corroded at all, and then they capture in real case, and then they give this as a difference, and when they do a normalization using this formula that has been plotted over here. But again we are able to see significant variation is not there. Of course we can say that this with the coating values are lower, the like a value is a lower here, value is a lower here, but the 10th month it was not checked. So this is the projected. Now naturally we really require much more sophistication, much more the data refinement to get a better value. Now what they have shown corrosion growth, we can say the photograph of corrosion exposure. This A has been shown, in this case A has been shown after 3 months, B is after 6 months, and C is after 10 months. So we are able to see the corrosion is growing, and at the last it becomes a loose particles also, and is a one is a spreading, and then a loose particle, and it takes off its own also, that goes beyond certain thickness, and it gets sheared off without its own. Here they did not do synergy, they did not do wear test on that, only the corrosion test itself. So when we combine we can really find out what is the overall results, because when we combine tribology with the corrosion, this wear rate will be much faster and much higher rate. So we really require those kind of results, and this will be discussing something in the lecture 18, which is on measurement analysis of wear debris. Reason being, when particles get dismounted from a surface, it will come as a wear debris. And how do we really modify these experimental readings and then make a much more meaningful results out of what we are getting? That will be covered in lecture 19, experimental design and statistical analysis. With this I say thank you for attending this lecture. Thank you.